In this video, we will see how we can apply the first derivative test to, in some situations, see that instead of having just a local max or min, we would have what we call a global max or min. That would be in terms of the entire domain of the function. You know, how small can it ever be, or how big can it ever be? So let's go ahead and just investigate as a motivating example the function x to the fourth minus 4x. So I need to find the critical points, which means differentiate and set equal to 0. So 4x cubed minus 4. I want to know what value of x is going to make this equal to 0. Both term has a 4 in common, so 4 times x cubed minus 1 equals 0. And the only way x cubed minus 1 can equal 0 is if x is equal to 1. So we have a single critical point of our function at x equals 1. And let's go ahead and apply the first derivative test. So I want to think in terms of a number line. We have a critical point at 1. And how is the sign of f prime behaving to the left of 1 versus to the right of 1? If we look at our first derivative and we plug in a large negative number, let's think, or actually 0 is in that interval, so let's just go ahead and plug in x equals 0. We would have 4 times minus 1, which is negative. So at x equals 0, we have f prime of 0 is equal to minus 4, which is negative. If we plug in something larger than 1, so let's think x equals 2, f prime of 2 is going to equal 4 times 8 minus 4, and the value is not as important as just observing this is positive. So if we think about what our function is going to look like, to the left of 1 it's always decreasing, and to the right of 1 it's always increasing. So decreasing, increasing. So we know that x equals 1 is a local minimum, and that's by the first derivative test. But we can say even more here. In fact, it has to be a global minimum. The reason it has to be a global minimum is because to the left of 1 our function is always decreasing, and then to the right of 1 it's always increasing. So it is not possible for the function to assume a smaller value anywhere else. So let's just kind of conclude here. Since f is decreasing left of 1 and increasing right of 1, f has a global minimum at x equals 1 with minimum value f of 1. If we go ahead and plug this into our function, the function is x to the fourth minus 4x, so f of 1 equals 1 minus 4, which is minus 3. And this kind of application of the first derivative test in some texts would be referred to as the first derivative test for absolute or global max and mins. If you have a single critical point, such as the situation here, and the first derivative changes there, say from negative to positive, that would guarantee instead of just a local min, an absolute or global min. If it was the opposite, where you went from increasing to decreasing, you would be guaranteed a global maximum. Let's investigate another example of global max and min with the function 1 over x squared plus 4. So I need to find the critical points and then hopefully classify with the first derivative test. So to differentiate, let me know you could apply the quotient rule, but this function f of x can be conveniently rewritten as x squared plus 4 to the minus 1, so that instead of applying the quotient rule, we can simply use a chain rule. So we take the derivative of the outside function, we evaluate it at the inside, and we multiply it by the derivative of the inside. So this becomes minus 2x over x squared plus 4 quantity squared. So exactly what you would find if you were to use a quotient rule. So use whatever method you prefer. And I want to know, where is this equal to 0? Well, fraction is equal to 0 when the top is equal to 0. So this happens precisely at the value x equals 0. So our function has a single critical point. Investigating this via a number line, we think, what is the sign of f prime going to be to the left of 0, to the right of 0? And the nice thing here to observe is that what's in the bottom is always positive. It's a square. So it's what's in the numerator which is completely determining the sign of f prime. So you think if I plug in a negative value of x, you have a negative times a negative, which gives you a positive. If I plug in a positive value of x, i.e. to the right of 0, I have a negative times a positive, which is a negative. So in terms of how our function is behaving, the first derivative is positive to the left of 0, which means it's increasing. And then everywhere to the right of 0, it's decreasing. So by the first derivative test, we would typically classify x equals 0 to be a local max. But in this case, since it's increasing everywhere to the left of 0, and decreasing everywhere to the right of 0, the only possibility is that at 0 is the absolute largest value this function can ever assume. So to conclude here, we would note that since f is increasing when x is less than 0 and decreasing when x is greater than 0, x equals 0 gives a global maximum value of f of 0. If we plug 0 into our function, we have 1 over 4. So the first derivative test guarantees a local max, but because it is always increasing to the left of 0 and decreasing to the right, we can furthermore say that local max is actually a global max.